Okay, and to finally summarize the last concept for thermal physics and engineering is to talk about entropy and how entropy influences the process of heat transfer. So in thermal physics, we learned that heat always transfers from hot to cold and not the other way around. And a lot of that is driven by the law of entropy, where the universe is always, there's a driving force to make things disordered. And the universe hates order. Okay, so when things are cold, the particles are all aligned, they're bonded. Okay, there's a lot of order in the system. When you put heat in, you cause them to vibrate, you cause them to separate, and you'll be increasing the disorder of the system. You'll be increasing the entropy, okay? So heat wants to go from something hot to cold to basically level out that entropy, to increase the entropy of the cold object. So here I have an example of an organized paperclip. Okay, and just explaining the disorder. As you start to bend it out of shape, you're increasing the disorder of the structure, and the universe will basically want to obliterate it and separate all the atoms out. And that's the rules of entropy. Okay, so entropy, the disorder of a system, increases during spontaneous processes. Those in chemistry would understand that. And this also explains why heat travels from hot to cold. Okay, there's that driving force. And because of that, your heat engine has to have a cold sink, as we just described in the previous process. We want to drive that energy out or drive it through the process. Okay, so that you can calculate the total change in entropy of a system. Let's say I had a piston. Okay, if I draw the piston, let's say I had a piston and I kept that piston at a constant temperature. Okay, and if I light a fire underneath and I put heat energy in, that's my Q. Okay, and that heat energy is doing something such that the system remains at a constant temperature. I could measure the change in entropy, which this process would be an entropy-driven process, okay, by measuring the amount of heat that I put in divided by the temperature of the system, okay? So the greater the amount of heat put in for that temperature, the greater the change in entropy of the system, all right? If heat flows into a system, if heat is flowing into that piston, the change in entropy is positive, and that piston is expanding by an entropy-driven process. Okay. On the other hand, if I'm contracting that piston, okay, and I'm doing work onto the piston, or I'm removing heat from the system, then the entropy is going to be negative. Okay. All right. So that will be a positive or negative, depending on how much heat is going out or going in. Okay. And then, if I want to be able to calculate the change in entropy of a heat engine, hot, cold, work being done, that's the cycle, okay? You would add up the heat that went through the system, that went in, so the heat that went in, divided by the hot temperature of the hot sink, plus heat that went in divided by the temperature of the cold sink, okay? And if you add that together, that would give you a change in entropy. If I rearrange this equation, I'd be able to come up with this one. Okay, so remember, if energy is going from the hot sink, it's leaving it, it's flowing out, so that entropy is going to be negative. And if heat is going into the cold, then that entropy is going to be positive. So the total amount of heat that was transferred between here and here, that's Q, okay, times 1 over Tc, that's positive because heat's flowing in, minus 1 over Th, that's negative because heat is flowing out. Okay, that would explain, if you did the calculation, let's say that this is 700 Kelvin and this is 300 Kelvin. If you plug that number in, let's say this is 10,000 joules of energy flowing through, okay, you'd be able to calculate the total change in entropy of the system, and it would be positive, which means it's a spontaneous process. Okay, it's favored. Okay, if the entropy was negative, that would mean that heat energy is going in the opposite direction, which is not allowed. That can't happen, okay? And that's basically it. That's it for the standard level engineering option, okay? I will continue to do a little bit more work with fluid dynamics and resonance for those of you that want to continue, but that's it. Thanks it's been a wonderful year, 2 years teaching you guys physics. It's been a lot, it's been a journey, ups and downs, and I hope that you've learned something about it, and I hope that in your lives, when you see physics out there, you'll remember maybe 1 or 2 of the concepts that we learned and maybe solve some of the world's problems. All right, good luck in your future.